Well, welcome, VESS scholars. In this module, you've been exploring the history of the universe, its formation, its evolution. You've also been exploring the formation and evolution of our solar system. And of course, in the context of that, you have to notice that there's a lot of things within our solar system, a lot of characteristics that have to be explained. And when we look at solar nebula theory, we can explain a lot of those characteristics, including the fact that they all orbit in the same direction, all orbit the sun in the same direction, all the planets, that is. Um, we can explain why there's terrestrial planets and gas giants and things of that nature. And we see a lot of these things play out in exoplanetary systems as well. So, of course, when we study the universe, we study the solar system or anything in space, or for that matter, in astrophysics, we tend to think of tend to use the cosmological principle as a guide. And there are three components to that. Just briefly: universality, homogeneity, and isotropy. Just focusing on that first one, universality. What it's saying in a nutshell is that all physical laws apply universally throughout the universe. And if this is the case, then we should be able to take Kepler's laws of planetary motion and apply them when we look at exoplanetary systems. Specifically in this lab, you're going to look at Kepler's third law. But of course, when you're looking at Kepler's third law, you're also looking at the first and the second law. But I get ahead of myself. Typically, when we look at the solar system, we look at it primarily as an image like this, where the bodies themselves might be roughly to scale in terms of their size, but their distance is not related really to scale. Here's another example where the bodies of the solar systems are depicted pretty much to scale, but the distances are not. So we call the semi-major axis, which will be an important term later on, is not accurately represented for these bodies in the solar system. On the opening slide here, it's much closer to reality, Pluto included here. Still not perfect, but it's closer to what reality looks like. Okay, Kepler's first law, and this is one of the things that's often not depicted correctly, just simply states that all planetary orbits are elliptical. And of course, an ellipse is defined by, as opposed to a circle, where that's defined by its radius. An ellipse is defined by a ratio between its major axis and its minor axis. The major axis being this long line, and this minor axis being the short line. And of course, we use a term called eccentricity to describe how eccentric or elliptical this ellipse really is. This is a pretty elliptical ellipse in this case. This might be more like a comet orbit or something along those lines. But it's exaggerated for the purpose of discussion. So what we call the semi-major axis is the distance we typically use for a planet from its distance from the sun to the outside of its orbit. The semi-major axis, of course, fluctuates, but we usually use an average. So we're looking at the average semi-major axis. So it's a part of the major axis, hence semi-major axis. An ellipse typically has, not typically, an ellipse always has two foci, where a circle only has one, and that's, of course, where the radius that defines the distance between the radius and the outside of the circle. The ellipse has two foci, and the sun will sit at one of the foci, and the other foci will typically remain empty. So, of course, the planet is orbiting along the path of the ellipse around these foci, but the sun being at one of them. That's Kepler's first law. Kepler's second law simply states, is really looking at the velocity of the planet and how it changes as it orbits. Because the second law states that as a planet orbits around a body, or let's say anything orbits around another body, it will sweep over. If you drew a line from that planet to the body it's orbiting, that line would sweep over an equal area in an equal amount of time. So in order to do that, across area 1, the planet, in this case, has to move. This is, of course, perihelion. At perihelion, its closest approach to the sun, the planet has to move a whole lot faster to sweep over that area than it does when it sweeps over from P3 to P4 in area 2. What ends up happening, if you watch this animated GIF, is that the planet moves much more slowly at aphelion than it does at perihelion. And that's Kepler's second law. Kepler's third law is the mathematical relationship that is the focus of this lab. And we'll get to the mathematical part of it here in a moment, but it's called the law of harmonies. Now, that seems like almost an antiquated term. If you're a historian of science, you know that scientists from the Renaissance love to give laws that they discover really interesting names. But the law of harmonies actually does mean something about harmoniousness within an orbital system. It's also sometimes referred to as the law of periods. But in an orbital system, the ratio between the square of any body's orbital period, t squared, and its distance, the cube of its distance, is the same for every body in the orbital system. Okay, which means that if that ratio when calculated for every single body in that system is exactly the same, they're harmonious. They agree on something, and that's really what harmonious is. It's agreement on something. In this case, their periods are all different, their distances are all different, but the ratio of the square of the period and the cube of the distance is all agree. So our argument would be that if for exoplanets, we know this works in our solar system, but if physical laws are universal and the universe itself is homogeneous and isotropic, then solar systems are likely very similar in appearance and composition and behave in a similar fashion when they exist around other stars. Of course, this also helps support solar nebula theory, and it helps us adjust that and make corrections to that as we learn more. Is the Kepler mission sensitive enough to pick this up, though? Are orbital transit curves accurate enough to be able to determine orbital periods and then calculate distances from those? Well, that's the job of the lab here. If they are, and you graph these two variables on a graph, you should end up with a nice linear relationship. Okay. So if we do this, we look at the Earth-Moon system, we look at the Sun and most of its planets here. We look at Jupiter and some of its moons. We calculate this ratio, and of course you can reverse the ratio. You can, as long as you keep the units consistent, it's all fine. But if you look at this for the Earth and the Moon system, you get a value. For the Sun and its bodies, you get the same values. They're harmonious. When you take the period cubed and you take the orbital radius squared, you end up, the orbital radius cubed and the period squared, you end up with the same value for every single planet. Same with the Jupiter system, you end up with the same value for these four moons. And if you did this for the rest of all 63 of its moons, or I think 63 last time I looked anyway, it tends to go up over time, you'd find that they'd be harmonious as well. But you'll notice these numbers aren't the same, are they? And that's an important thing to point out. And it connects Kepler's third law. Now, of course, Kepler discovered this before Newton discovered, really kind of calculated gravity and determined what was going on with that. So you can use the law of mutual gravitational attraction to derive Kepler's third law. And indeed, that's what you see going on here. So the reason these numbers are different is because the parent body, in this case, the Earth, the Sun, or Jupiter, all have different masses. If you were to have these objects all orbiting the Sun, then you would have this ratio over here, and if you had them all orbiting Jupiter, then you'd have this ratio over here, and that's how this works. So it's dependent upon the mass of the main body that is being orbited. So likewise, if you're launching a satellite into orbit, and you want it to orbit in a geostationary orbit, so one revolution, then you're going to have a particular ratio that works for any satellites orbiting the Earth. They're going to have the same ratio. Okay, moving on. For the lab, you are going to use the Kepler 11 system, which is a not so far away exoplanetary system with a number of planets. I'll point out that in an exoplanetary jargon, when you look at Kepler B, C, D, E, and so forth, Kepler A is the star itself, B is the first planet, followed by C, and so forth. So the higher the letter, the more inner the planet is, closer to its star. But A is always the star, so you don't usually see a Kepler. You won't see a Kepler A in this case. But you're going to see whether Kepler's law of harmonies works for the Kepler 11 system. It's nice how we're sticking with the name Kepler here, isn't it? Kepler's laws, Kepler mission, and Kepler 11 planetary system. Is this law universal? You're testing its universality. You're also looking to see whether there's this universality can say something consistent about solar system formation and development, and whether our solar system is different in the way planets orbit than other solar systems. These are big questions. These are really powerful questions. If this law is universal, then it should also work in other planetary systems, and it's your job to find out. In order to do that, of course, you're going to go to a website that is linked to your from your lab. If you read the lab description, you'll see the link there, and it'll talk about the link, and you'll see it, and you can go in and get the data you need for the lab. And once you get all the data put into the chart, you can make a simple calculation and see whether all the numbers are all the same, and whether that system really is harmonious based on Kepler's third law. Until next time, enjoy.